Yes, Section 240.4d of the National Electrical Code applies to motor conductors. To understand this, it's important to consider the structure of the NEC and how it addresses different aspects of electrical installations. The NEC is divided into several parts, each covering specific areas. Part Roman III addresses wiring methods, materials, and equipment for general use. Part Roman IV focuses on wiring methods, materials, and equipment for power distribution and utilization systems. Part V covers special occupances, while Part VI addresses special equipment, and Part Roman VII deals with special conditions. Because motor conductors are integral to power distribution within a system, the regulations in Part Roman IV are relevant. Section 240.4d resides within Part Roman IV. This section outlines the requirements for overcurrent protection of conductors. Specifically, 240.4d addresses the protection of conductors rated 0 to 2000 volts. It mandates that the ampacity of these conductors must be determined by referencing Table 310.16 and applying the correction and adjustment factors as outlined in Tables 310.15b16 through 310.15b20. Table 310.16 is a crucial reference for determining the allowable ampacities of conductors based on their size and insulation type. For instance, it specifies the ampacity of copper conductors of various American wire gauge sizes such as 1412 and 10 American wire gauge. According to Table 310.16, a 14 American wire gauge copper conductor typically has an ampacity of 15 amps. A 12 American wire gauge copper conductor has an ampacity of 20 amps, and a 10 American wire gauge copper conductor has an ampacity of 30 amps. It's essential to consult the specific table within the NEC to account for the insulation type and temperature rating of the conductor. These ampacities are based on specific conditions, and dating factors may need to be applied based on ambient temperature, the number of conductors in a raceway or cable, and other relevant factors outlined in 310.15b16 through 310.15b20. The NEC provides guidance on how to apply these correction and adjustment factors. Therefore, when sizing motor conductors, you must refer to Table 310.16 to determine the appropriate ampacity for a given conductor size. For example, if you are using a 12 American wire gauge copper conductor, you would typically refer to Table 310.16 to find its ampacity, which is generally 20 amps. However, remember that you must also consider any dating factors that may apply based on the specific installation conditions. In summary, Section 240.4d does apply to motor conductors, and Table 310.16 is the primary reference for determining their ampacity. Always consult the latest edition of the National Electrical Code and consider all applicable correction and adjustment factors to ensure that motor conductors are properly sized and protected. The proper sizing of motor conductors is essential for ensuring the safe and reliable operation of electrical systems. Using conductors that are too small can lead to overheating, insulation breakdown, and even fires. On the other hand, using conductors that are too large can be wasteful and expensive. Therefore, it is crucial to carefully consider all of the relevant factors when sizing motor conductors. The following are some additional factors to consider when sizing motor conductors. Firstly, the motor's full load current rating, which can be found on the motor's nameplate. Secondly, the NEC requires that motor conductors have an ampacity of at least 125% of the motor's full load current rating. This is to account for the fact that motors can draw more than their rated current during starting and overload conditions. Thirdly, the voltage drop in the conductors. Excessive voltage drop can reduce the motor's performance and efficiency. The NEC recommends that the voltage drop in motor conductors should not exceed 3%. Fourthly, the ambient temperature and the number of conductors in a raceway or cable. As mentioned earlier, these factors can affect the ampacity of the conductors. Fifthly, the type of insulation on the conductors. Different types of insulation have different temperature ratings. It is important to choose conductors with insulation that is suitable for the operating temperature of the motor. By carefully considering all of these factors, you can ensure that motor conductors are properly sized and protected, and that the electrical system operates safely and reliably. Here's a more detailed explanation of how to apply 240.4d in Table 310.16 to motor conductor sizing. Firstly, determine the motor's full load current FLC. This information is found on the motor's nameplate. It's crucial to use the correct FLC value for the motor's voltage rating. For example, a motor rated for both 230 volts and 460 volts will have different FLC values for each voltage. Always use the FLC that corresponds to the voltage at which the motor will be operating. Secondly, calculate the minimum ampacity required for the motor conductors. According to the NEC, the minimum ampacity of the motor conductors must be at least 125% of the motor's FLC. This is to account for the motor's starting current and potential overload conditions. To calculate the minimum ampacity, multiply the motor's FLC by 1.25. For example, if a motor has an FLC of 10 amps, the minimum ampacity required for the motor conductors would be 10 amps times 1.25, which equals 12.5 amps. Thirdly, select a conductor size from Table 310.16 that has an ampacity equal to or greater than the calculated minimum ampacity. Table 310.16 lists the allowable ampacities of various conductor sizes based on their insulation type and temperature rating. When selecting a conductor size, make sure to consider the insulation type and temperature rating of the conductor. The conductor's insulation type and temperature rating must be suitable for the operating environment. For example, if the motor is located in a hot environment, you will need to use conductors with a high temperature rating. Fourthly, apply any applicable correction and adjustment factors from Tables 310.15b16 through 310.15b20. These tables provide factors for directing the ampacity of conductors based on factors such as ambient temperature, the number of conductors in a raceway or cable, and the presence of other heat-generating equipment. If the ambient temperature is higher than the temperature listed in Table 310.16, you will need to apply a correction factor to reduce the allowable ampacity of the conductor. Similarly, if there are more than 3 current-carrying conductors in a raceway or cable, you will need to apply an adjustment factor to reduce the allowable ampacity of the conductors. Fifthly, verify that the selected conductor size is adequate for the application. After applying all applicable correction and adjustment factors, make sure that the ampacity of the selected conductor size is still equal to or greater than the calculated minimum ampacity. If the ampacity of the selected conductor size is less than the calculated minimum ampacity, you will need to select a larger conductor size. In addition to these steps, it is also important to consider the voltage drop in the motor conductors. Excessive voltage drop can reduce the motor's performance and efficiency. The NEC recommends that the voltage drop in motor conductors should not exceed 3%. To calculate the voltage drop in the motor conductors, you will need to know the length of the conductors, the conductor size, and the motor's FLC. There are several online calculators and software programs that can help you calculate voltage drop. If the voltage drop exceeds 3%, you will need to select a larger conductor size or reduce the length of the conductors. Here's an example of how to apply these steps to size motor conductors. Assume a motor has a full load current FLC of 20 amps and will be operating at 230 volts. The conductors will be installed in a raceway with an ambient temperature of 30 degrees Celsius. The conductors will be type THHN copper conductors. Firstly, calculate the minimum ampacity required for the motor conductors. The minimum ampacity is 20 amps times 1.25, which equals 25 amps. Secondly, select a conductor size from Table 310.16 that has an ampacity equal to or greater than 25 amps. According to Table 310.16, a 12 American wire gauge THHN copper conductor has an ampacity of 30 amps. Therefore, a 12 American wire gauge conductor would be suitable for this application. Thirdly, apply any applicable correction and adjustment factors from tables 310.15b16 through 310.15b20. In this case, the ambient temperature is 30 degrees Celsius, which is the same as the temperature listed in table 310.16. Therefore, no correction factor is required. However, if there were more than 3 current-carrying conductors in the raceway, an adjustment factor would need to be applied. Fourthly, verify that the selected conductor size is adequate for the application. The ampacity of the 12 American wire gauge conductor is 30 amps, which is greater than the calculated minimum ampacity of 25 amps. Therefore, the 12 American wire gauge conductor is adequate for this application. Finally, check the voltage drop in the motor conductors. This example illustrates how to apply 240.4D in table 310.16 to size motor conductors. By following these steps, you can ensure that motor conductors are properly sized and protected, and that the electrical system operates safely and reliably. Remember to always consult the latest edition of the National Electrical Code and to consider all applicable local codes and regulations.